Swayam Prabha. Digital India. Educated India.
Hi everyone, welcome back to another lecture of this course on robust control, and we shall continue to see what we've been doing over the last one or two lectures today. That is, we shall look at this notion of certain topological notions that we just began to introduce very recently, maybe in the previous lecture. So the one notion that we have seen is that of a neighborhood. Just to put things in context, why are we interested in all of this? Our end game is to understand ideas such as convexity, right? And why is convexity important? Because in this context of this course of robust control, we shall see that we will be dealing quite frequently with problems of the optimization variety, right? So we shall be trying to optimize certain things. There will be some objective function which we want to optimize subject to certain constraints. And more often than not, we shall encounter convex optimization problems. So therefore, it is imperative that we understand the notion of convexity, and in order to understand this notion of convexity and separating convex subsets within a vector space, we need to understand certain topological aspects of vector spaces. That is precisely the motivation behind delving into these topics such as the ideas of neighborhoods, these open balls, open sets, closed sets, etc. So today we shall continue to see some more of those ideas until we feel that we've covered more or less all the relevant ideas of topology of a vector space, and then we shall move over to the very important idea of convex subsets, convex hulls, convexity itself, and we shall see what convexity generally entails, why we like dealing with sets that are convex rather than those which are not convex. Okay. For those of you who have some ideas or some introduction to optimization problems, you probably already know by now that, well, it's a totally different ball game when you deal with optimizations problems that are non-convex in nature, right? Okay. So with that in mind, let us proceed. Now the last day in the previous lecture, we've seen this idea of a neighborhood of the origin. Okay. So to quickly recapitulate what we've done in the previous lecture, insofar as this idea of neighborhood goes, we have a vector space that we have defined, and we say that suppose there is a basis that we've chosen, and this basis is not something specific, right? You are free to choose your own basis. Now, subject to this particular choice of basis that you or I might have made, we define something called a unit ball. What is this unit open ball? We'll come to the idea of open and closed sets in a bit. So what is this unit ball that we've defined here? Unit ball is something that is a set containing vectors of the form alpha 1 u1 plus alpha 2 u2 so on till alpha n un, where of course u1 through un form that basis for the vector space, right? Such that the sum of the squares of these alpha i's is less than unity. Okay, so that is a unit ball, not necessarily something that looks spherical, right? Okay, I mean, of course, we are dealing with abstract vector spaces, so even the idea of a spherical ball in that sense makes no sense unless you really relate it to a Euclidean space. Okay, but that we have seen we can do that using this idea of coordinates. But even if you do use the idea of coordinates, so long as these coordinates are not orthogonal to each other, you don't have an orthonormal basis. Yeah, it need not look like a spherical ball, okay, but nevertheless we call it a unit ball. And naturally the size of the unit ball is also not specified, because we have not said that the elements in this basis, yeah, that they have to be that they have to be of a certain particular norm, right. Okay, I think I kind of see that there should be a correction there. So, probably I defined the basis in terms of V's and suddenly I wrote U here. So, let me just correct that. Yeah. So, these are V's. Okay. So, of course, as I said that if you choose a basis V1, V2, V3 till Vn, someone else may choose a basis T1 V1, T2 V2, T3 V3 till Tn Vn, where all these Ti's are not equal to 0. And in that case, the size or the norm of these individual elements in the basis, they can vary. So will the size of the unit ball accordingly, right, as you might guess. Just try to relate this to the notion of Euclidean spaces and you will immediately see the 2D and the 3D spaces, right. Okay, so that Euclidean, that sense of, sorry, not the Euclidean, that sense of unit ball seems pretty arbitrary because it depends heavily on the choice of basis. As it turns out now, based on this notion of the unit ball, we can now get to a definition of what is called a neighborhood of the origin. So, how did we define this? We called a subset to be a neighborhood of 0 or the origin if there exists some basis, okay, some basis say V1, V2, V3 till Vn such that the unit ball defined in terms of that basis is contained within that set, and that set which contains the unit ball is then the neighborhood of the origin. You can immediately check that within this unit ball the origin is also itself contained. That is quite obvious, no, right, because obviously you choose alpha 1, alpha 2, alpha 3 in this yellow boxed expression, you choose alpha 1, alpha 2, each of them to be 0, and you get this point, that is the origin. So, of course, the origin is a part of its own neighborhood, needless to say, right. So, the point is that if you choose a subset around the origin in some sense, such that subject to some choice of basis, you can get this subset to contain the unit ball defined in terms of that basis, then that set is indeed a neighborhood of the origin. Now, notice something beautiful here. Although this unit ball is very heavily dependent on this idea or the choice of this basis, the neighborhood actually gets rid of the specificity of the basis. Why? Because I am saying there exists some basis. So, you are allowed to choose any basis and correspondingly any unit ball, right. So, how you define a neighborhood, you might choose some basis, I might choose some other basis, we will get different unit balls, but that really has no bearing on whether a particular set can be called a neighborhood or not. So long as each one of us can choose at least one basis such that the unit ball defined in terms of that basis is contained within that set, then that set qualifies as a neighborhood, okay. So this leaves no room for ambiguity, right, that you cannot say that, well, because we choose a different unit ball, the neighborhood will also depend on that unit ball. No, it does not. So long as both of us can find any basis for which the corresponding unit ball is contained within that set qualifies as a neighborhood. So if I manage to find one such basis, then that guarantees the existence of such a basis and therefore it qualifies as a neighborhood, full stop. Your failure to find such a basis does not disqualify this set from being a neighborhood, right. So that is very important. So in the definition of the neighborhood, because you are allowed to search over all possible bases, the choice of a specific basis does not qualify or disqualify this neighborhood or this set from being a neighborhood or not, okay. Any basis, the existence of any one particular basis such that its unit ball is contained within that set qualifies this as a neighborhood. Important point, okay. We will keep on clarifying these points even at the risk of going a little slowly and probably boring you, because these are fine notions in the abstract vector spaces which we really need to grasp, like what is the critical point in each of these definitions, okay. So the next important thing that we want to describe now that we have defined this neighborhood of the origin, can we extend this idea to the neighborhood of any arbitrary point? Because in so far as a vector space is concerned, the origin is very special, Yeah, it's the smallest subspace contained within the vector space. But insofar as the idea of a neighborhood is concerned, I am not really concerned about subspaces, right. When I say something is a neighborhood, I am dealing with subsets. This neighborhood n of 0 is a subset. I am not desirous of any specific properties of vector spaces to be met by this subset. So therefore, can I not extend the idea of a neighborhood to any arbitrary point in the vector space rather than just restrict myself to defining the neighborhood about the origin? Well, it turns out we can, and the way to do that is very commonsensical. The idea of translation that we are all very familiar with. So here goes. Suppose you call this set n of w. So this is a subset, remember this n of w. So suppose this n of w is a subset contained within the vector space V, yeah, and this is a neighborhood of not the origin but this point w, this vector w in the vector space V, yeah. What does it then satisfy? If, notice very carefully, I define this another subset n, which is basically a collection of all vectors V in the vector space V, such that when I add this specific vector w, when I add this specific vector w to every element in that set n, that is of the form V, yeah, then this V plus w, this fellow belongs to nw, yeah. So what have I defined? Just take a moment to pause here. I have not yet completed the definition of the neighborhood of w, but I will take a moment to clarify what this description of this set means. You may not be very familiar with such set theoretic descriptions. What this basically means is, what is this n that I have underlined with two red lines? This n is basically a collection of vectors in the vector space V, such that, that colon means such that, when you add, now remember this w is given to me. So first I have already without any ambiguity defined to you what the neighborhood of the origin is. Now I want to extend this idea of neighborhood to any arbitrary vector or arbitrary point w in the vector space. Okay, so w is known to me. W is a fixed vector, okay, not variable. W is a fixed vector. Now what I am saying is, let me choose arbitrary vectors V and add them to w such that V plus w belongs to this set nw. Okay. So I am not allowed to choose any arbitrary V then, right? Am I? Because if I choose any arbitrary V in V, then it will just be the entire vector space V. So I am restricting my choice of vectors within the vector space V to only those vectors such that when I add, you know what vector addition is, needless to define, right? Because we already know in the definition of vector space what addition is. So what I am saying is, I will choose specifically those vectors in the vector space V which when added to this particular vector w about whom I am supposed to find the neighborhood, yeah, such that when V plus w, this resultant vector, belongs to this set nw. So that is what this set n is, yeah. But this is not the end of the story. This n needs to satisfy. So remember, this is a part of a sentence. This is dangling now. I have not completed the sentence yet. When will the sentence be completed? If this set, so what does this set contain? This set contains vectors in V, certain particular vectors, specific vectors in V, not all of them, only those vectors in V. So what have I been given? I have been given a set nw and I have been asked the question. So think of it like this, I have been given a set nw, yeah, and I have been asked to check if this nw is a neighborhood of w. So then I want to define what the neighborhood about w is. So here is the acid test, okay. So I figure out all these vectors V which when added to this w vector is known to me. So I add them and I get the resultant vector and I check if the resultant vector belongs to the set nw. If it does, then the original vector V that I had picked belongs to this set n. Okay. So, given W and NW. So, what are given to me? I have been given this vector W and I have been given this set NW, and the question before me is whether NW is a neighborhood of W. This is what the definition will answer. Okay. So, if I have understood the definition well, then given any vector W and a set or a subset of the vector space NW, I should be able to answer as to whether NW indeed is a neighborhood of W. Okay. So, what do I do? Given W and NW, I keep adding vectors V to W and check whether those vectors belong to NW. If they do, then I retain those vectors V and collect them together. If they do not, I discard those vectors. So, likewise I retain some collections in my basket, and that forms this yellow box, this subset N. Okay, it is a collection of all those V's. Now, once I have got my entire collection of such V's, I have to run a test. If this collection that I have now got satisfies some condition, what condition? And here is the crux of the matter. If this N that I have now obtained from NW and W, from NW and W I have cooked up N, and this N is a neighborhood of the origin, or in other words we say that N, so N qualifies as a N0, but okay, we have already written it in words, so let it be. So, what I am saying is, given a W and an NW set which I have to check for whether it qualifies as a neighborhood of the point W or not, I collect all those V vectors which when added to this given W lead to a resultant that belongs to NW. NW is given, W is given. So, I can check whether this vector belongs to NW. If it does, then I collect that V and put it in a basket. So, I collect together all these V's and put them in this basket, and then that basket I label as this N, right. And then once I have got this basket filled with all possible candidates, I have filtered them out, then I run this basket through a test. What is the test? I figure out whether this basket qualifies as a neighborhood of the origin. And is it a very hard test to check? I already know what the neighborhood of the origin is. I have just defined it in the previous class, right, in the previous lecture. So, now I run the test whether N qualifies as a neighborhood of the origin. If it does, then this set NW that I had been given, this subset NW of the vector space that I had been given, indeed qualifies as a neighborhood of this vector W. That is it. That is the notion of neighborhood of any arbitrary point in a vector space. Okay, very, very important notion. Okay, because this idea of neighborhood, and what does a neighborhood contain? A neighborhood of the origin, it must contain some open unit ball, which means that there exists some basis. Just try to piece together these ideas, take a pause at this point, and just try to get these ideas streamlined. It takes a while to settle down, but once it settles down, it is really quite easy to see, not very difficult, rather straightforward. Okay. So, once we have explained these ideas, next we have to define, after all I have briefly mentioned this in passing, that we call this an open unit ball. So, what is this idea of openness? What is this open set after all, right? So, we have defined this idea of what we call neighborhood of a point in the vector space. So, now we get this idea of open and closed sets. Okay, this is the next important idea that we need to get a handle on. So, what is an open set? So, let us say, again we will not define these very formally, but we will try to explain them in as lucid a manner as possible. So, suppose Q is an open set. What does it mean? What property must it then satisfy? So, you will come across statements like these that suppose Q is an open set. Now, we want to understand what is this idea, what should we immediately infer from this statement that Q is an open set. So, that means immediately what it should strike you as is, that means there exists a neighborhood of V which is contained in this set Q. Yeah. So, for all V, for any arbitrary V that you can pick out in Q, yeah, maybe I should have put this first, but anyway I have managed it. I am anyway writing in a very semi formal manner. So, what does this statement mean? What I am trying to explain now is, when someone says that Q is an open set, what must you immediately read between the lines? What should immediately flash in your mind then is that it means you know what a neighborhood is. Yeah. So, immediately you will infer that for every point or every element in that open set or in that set Q, yeah, you can create a neighborhood around that point, yeah, such that, so you know what the neighborhood around a point is now, we have already seen that idea. So, here is how we started. We saw the neighborhood about, we saw first an open ball, a unit ball rather, yeah, how it is defined in terms of basis. Then based on that idea of the unit ball, we saw what the neighborhood about the origin is. If it contains some unit ball about subject to some choice of basis, then it is a neighborhood about the origin. Then we saw that we can translate that neighborhood about the origin by a vector W to get the neighborhood about the arbitrary point W. And now, using this idea of a neighborhood around any arbitrary point in a vector space, we say that if a set is such that around every point in that set you can construct a neighborhood, yeah, such that the neighborhood that you have constructed, so some neighborhood, remember the restriction here is that you might have to make a very small neighborhood. Nonetheless, even if the neighborhood is very small, right, that means the unit ball that you are trying to cook up is even smaller probably because it is contained within that neighborhood. So, then such that this neighborhood is entirely contained within that set Q, yeah, then we say that it is an open set. So, the moment someone says it is an open set, it means that there exists a neighborhood of V for every point V that you can pick out, every potential point V that you can pick out in that set, there exists some neighborhood of it such that this neighborhood is entirely contained within that set. So, what sort of sets, let us just give the contrary example, what sort of sets would typically, I mean pictorially at least, although I hate drawing pictures, but let us just do it for the sake of it, yeah, here. So, what sort of a set? So, think of a set like, you know, a set that looks like this and includes points on the periphery, right. Suppose it includes a point on the periphery like this. Now, try to imagine this, no matter what sort of a, so you have basis vectors in different directions, right. Again, for want of space, you know, I will just draw 3 because that is the most we can think of, 3 dimensions. Beyond 3 dimensions we can't even visualize. That is the reason we do these abstract ideas, we push them through. But anyway, so that is why I always feel drawing a picture defeats the purpose, but somehow it also helps in visualizing. So, let me go ahead and violate my own, I mean something that is not to my taste really, but anyway. So, suppose you have this particular basis. Now, subject to this basis, if you want to draw a ball, then this ball would look something like this, and then a neighborhood must contain this ball. So, a neighborhood must be at least larger than this. But note that if you contain a point on the periphery like this, then can such a neighborhood be entirely contained within the original set? Of course not. In some direction there would be a vector which would take you away from the periphery of that set, and because of that vector existing, yeah, you see if all your vectors are pointing inwards, then there is no vector pointing outwards, and therefore that will not form a basis set, right, because then any vector along a direction that is outwards to this tangent of this set here that I have drawn, yeah, that vector will not be spanned by this set, therefore it will not be a basis. If it is not a basis, then it cannot form a unit ball. If it cannot form a unit ball, again very loosely speaking I am doing all this, if it cannot form a unit ball, yeah, then you cannot push your idea of a neighborhood through. right. So, therefore, any neighborhood of a point on the periphery of such a set cannot be entirely contained. On the other hand, if I draw the same kind of object with dotted lines here, so I am saying that this contains all the points interior or inside, however you understand this, okay. Again, these are technical terms, but suppose you do not allow points on the periphery, but apart from that you exclude the periphery and you contain everything inside. So, it is like a potato you can think of, and you exclude all the points on the peel, yeah. So, if you could have peeled the potato, yeah, and then everything that is exactly the potato which you actually want to cook, then that is what you are talking about, you have taken the peel off, right. So, now you again reconstruct, do some reconstructive surgery to put the peel back on, and then you say that everything other than the peel of the potato is my set. Then you see that no matter how close you get to the peel of the potato, you will always be able to find a neighborhood. Why? And this is what the basis of calculus is after all, right. You always take these incremental advances and you say that, okay, I can get close to the periphery, but unless I am exactly on the periphery, there is always a non-zero distance between that point and the periphery, and therefore you can always choose a vector that is small enough but pointing outwards. And so you can choose a unit ball that is entirely contained within this particular set, and therefore you can also choose a neighborhood that is also entirely contained within. Of course, the neighborhood might be slightly bigger, but if you choose the ball to be slightly smaller, then you can fit in the neighborhood also within this. So, there exists some neighborhood, yeah. So, that is what we are trying to find out, that if you can guarantee that such a neighborhood will always exist, then it is an open set, okay. And quite simply, any set that is not open is a closed set. So, the idea of a closed set is very easy, right. So, any set that is not open is a closed set. So, for example, the complement of an open set is a closed set, okay. So, suppose you have Q, suppose Q is an open set, then define Q complement as all those vectors V in the vector space V such that V does not belong to Q, yeah. Then Q complement, so this is an example, right. So, I am just cooking up an example. So, then Q complement is a closed set, okay. So, the moment you have an open set, hand in hand with an open set comes the idea of a closed set, okay. No doubts about how to figure out if a set is closed, just look at its complement. If the complement is open, then you can say that the original set is closed, okay. This is just a very simple trivial example to cook up, alright. So, now we want to get something called a, okay, let me use the same color. So, closure of a set, this is the next idea that we shall see. So, what have we seen so far? We have seen neighborhood, we have seen neighborhood about a point, and now we have moved on to open and closed sets. We have understood what open and closed sets are. Now, given any set, it need not be open, right, or it need not be closed, it could be open or it could be closed, any. But for any arbitrary set, we can always define something called the closure of that particular set. So, what is the closure of that particular set? So, define Q bar the closure of the set Q in the following manner. So, for every set Q, let me denote, or let us say, let me not say define, okay, yeah, this is actually a definition. So, I am denoting this by Q bar and I am defining it thus. So, what is going to be my definition? Pay very careful attention. Once again, it's going to be a little heavy on the set theoretic notation, but hopefully by the time I explain to you what this notation means, yeah, and by we should really try to get familiarized with this idea of set theoretic representation of objects. Yeah, that's another of the central ideas of this course. Okay, so what is the closure of this Q? So then Q bar is defined in the following manner. It is a collection of all those vectors in the vector space V such that for all neighborhoods that you can think of, yeah, of V, we have the condition that the intersection between the neighborhood and the set Q is going to be non-empty. Yeah. What does this mean? Let us go over this slowly again. Okay. You have this original set Q, alright. Now, you pick out these elements in the vector space V such that the moment you construct a neighborhood around this point or this vector V, yeah, and if you take its intersection with the given set Q, then it is going to be non-empty. So, what is the main crux of this matter here? What is the main thing that I am trying to hint at here? Yeah, what I am saying here is that, well, if you choose a large enough neighborhood, then it is really not a challenge. I mean, a large enough neighborhood would often, intersect with this set Q. It is only when the neighborhood is really small, yeah, that is when it becomes a challenge. Like when I choose a really small neighborhood around a point V, yeah, does it still intersect? Yeah, does it still intersect with this particular open set Q that I have been given? So, again, at the cost of violating my own kind of unspoken or unwritten rules, let me try to draw a figure for this. Okay, suppose this is a set, or maybe maybe an open set. Yeah, maybe an open set. So, I do not include the peel of the potato or the boundary. And let us say I pick a point over here. I pick a point over here that is outside this set. Obviously, I can always create a small enough neighborhood around this. Yeah, I can always create a small enough neighborhood around this point, because this is a legitimate point in the overall vector space, no? So, this is my set Q, just let me put this here. So, this is my set Q, right. This Q is sitting inside a vector space and this point is a point V. Yeah. So, does this point, do you think this point V then qualifies as a point that belongs to Q bar, the closure of Q? No, because I have found at least one neighborhood. Yeah. So, there is no restriction on what sort of a neighborhood I can choose. It says all neighborhoods of V, right. So, I have found one small enough neighborhood of V such that that neighborhood is completely disjoint from this set Q. There is no overlap, right. So, therefore, this point does not qualify as a member of this set Q bar, and therefore, it does not belong to the closure. On the other hand, if you choose a point that is entirely inside this, then no matter what sort of a neighborhood you choose, because that neighborhood must contain the point itself, there must be something common between the neighborhood and the set Q, and therefore, it has a non-trivial intersection, right. So, therefore, it must be part of the closure. So, anything that belongs to Q must be a part of its closure. So, therefore, we have this conclusion that Q must be contained in the closure of Q. Yeah, that's an obvious conclusion you can draw, right. So, Q must be contained in the closure of Q. What about points that lie on the periphery, or like the points on the peel of the potato, as it were? look, now this point on the boundary itself does not belong to this set Q, because Q is an open set, so it excludes its boundary. But can you draw any neighborhood, can you cook up any neighborhood about this point on the periphery such that it does not include any point inside this set? Of course, again, be very warned that whenever people draw these pictures, they want to fool you, even myself included here. So sets need not look like this, okay. This is just a pictorial depiction of a set. You can cook up different types of sets which look nothing like this. So what an argument that appears very convincing when I draw a figure like this may be completely off, right, may not work as a general proof of a statement. So what I am giving you here is a flavor of why something is true, not necessarily a rigorous proof of these facts, okay. Be very warned that after you finish off or you finish watching today's lecture, do not go with the mistaken impression that you have actually seen proofs of certain results. These are not by any means the proofs of these results. If you want detailed proofs, you should actually take up a book on topology. There you would find these standard manners of tackling these proofs, okay. We are, however, not concerned with such rigorous proofs, just we want an intuitive understanding of these so that we can employ them later on in our course. So it is important to understand these notions, but the proofs may not be so essential for the purpose of our particular course. Nonetheless, the ideas should be clear. Okay, so back to this argument. Now, around this point on the periphery, if you notice, you cannot construct any neighborhood of this about this point which does not overlap with the set Q at all. In other words, that intersection cannot be empty. So therefore, points on the boundary, irrespective of whether the set is open or closed, and this is interesting because now even if a set is open, its closure is always going to be a closed set, right? Because if it weren't, if it has, if it were actually an open set, yeah, then you take points on its boundary, yeah, which make it a closed set, yeah, and then you see that those those points will actually belong to the closure, right? So therefore, you see that this closure will include points on the periphery of a set even if the set is an open set. So therefore, in general, for an open set, a closure is strictly going to contain more elements than the open set itself. So in case of an open set, if Q is an open set, then Q is strictly contained within its closure. So that means its closure strictly has more elements than are contained in the original open set Q. Yeah, that is essentially the take home message from this, right. So the critical thing here is that when you choose this for all NV, what sort of NV are we trying to look at? Howsoever small. Yeah, this is very important. When you say for all sorts of NV, when does the case become challenging? When you choose large neighborhoods, intersecting the set Q with large neighborhoods is not a challenge. But what if you keep making this neighborhood smaller and smaller, smaller and smaller? Will they still intersect with this set Q? If they do, no matter howsoever small you make this neighborhood, then it qualifies as belonging to the closure, right? Then it is a member of the closure of this set, alright. So every time you are allowed to choose any object, try to find out when the case becomes more challenging, right? What sort of objects are more challenging, right? So what sort of neighborhoods are going to be challenging case? When you make the neighborhood smaller and smaller, then the question becomes critical as to whether this intersection is still non-trivial or not, yeah, non-empty or not. Okay. So now that we have seen the idea of this closure, we will move over to the next important idea. Okay. So what is the next important idea? Next important idea is that of disjoint sets. Of course, we intuitively understand what disjoint sets are. So if we are given two sets Q1 and Q2 and asked to check if Q1 intersection Q2 is equal to the empty set. Yeah. How do we go about this? That is the question. How do we formally go about this? You see, it's not a very easy question to answer, right? I mean, intuitively we might feel that, yeah, given two arbitrary sets whose natures we understand, which are well defined, we should be able to get this. Well, it's not easy. Yeah, it totally depends on the topology, right? So how do you find out? Look, if you think of it for a moment, this is like an infinite search. Yeah, you might have given me 10,000 examples of elements that do not belong to this intersection, but I might find a 10,001st element which actually belongs to both Q1 and Q2, and then your hypothesis would have fallen apart. Yeah, so these kind of tests are very difficult in general, right? You might have searched and cooked up lots and lots of examples of elements which do not belong to this intersection, and then you might have reasonable grounds to believe that indeed this intersection, you have searched almost all plausible, so called, according to your opinion, all plausible vectors or elements which could have been members of both these sets, and you found that they weren't. So you might have good reasons to believe that Q1 intersection Q2 is indeed empty. Yeah, but you might have missed something. Who is to guarantee that? Yeah, you have to be really exhaustive in order to guarantee that. So I might find one element and your entire hypothesis falls apart, and all the effort you have put in behind checking for each of those 10,000 elements or maybe even million elements, yeah, it's wasted, right? So that's why this type of tests which harp on or which rely on these sort of definitions, yeah, they are very hard to perform in general. So we need to adopt a little more formal approach towards this. This is not a question that is to be taken lightly. So how do we go about this checking? So we say that Q1 and Q2, which are both, let us say, subsets of this vector space V, and we introduce this notion of what is called strictly separated. Yeah. So if they are strictly separated, then there is no way that their intersections can be anything but empty. Yeah. So if there is a way to check for this strictly separated condition between two subsets of a vector space, then we would have answered this question. So here is the way to do it. Here is the way to check based on all the tools and mechanisms that we have now developed, or these definitions that we have developed or given you. It turns out that there is a formal way of describing this. So if you have two sets in an underlying vector space, yeah, and they are strictly separated, then a sufficient condition for checking the strict separateness is that there exists a neighborhood of the origin such that for every V1 belonging to Q1 and for every V2 belonging to Q2, yeah, we have V1 minus V2, yeah, does not belong to that neighborhood of the origin. Let us again go over this slowly and try to understand what this means. What it is saying is that if you have two sets, Q1 and Q2, and you are allowed to choose any arbitrary element from Q1 and any arbitrary element from Q2, right? What do you do? Because these, remember, these Q elements in Q1 and Q2 are also elements in V. So the idea of vector addition and subtraction are valid for elements in Q1 and Q2 both. So you can take an element in Q1, you can take an element in Q2, and you can subtract them because they are both essentially coming from the same vector space V. So you pick any arbitrary element in Q1, any arbitrary element in Q2, yeah, take their difference, okay, that will be another vector in V. Now check if this vector V does not belong to some neighborhood. Again, very subtle point. So, yeah, so again this is this n0, this neighborhood is something that you have to construct. So again let us try to pose this as a challenge, what have been given to me and what I have to find out. So I am given the set q1, I am given the set q2, alright. The challenge before me is to find out this object that I have boxed in red, this neighborhood of the origin, such that irrespective of which element I pick from set q1 say v1 and which element I pick from set q2 say v2, their difference will not belong to this neighborhood. Why is finding this neighborhood challenging? If I allow this neighborhood to be large enough, yeah, then I will figure that, well, even two vectors v1 and v2 which are not very close to each other, the difference between the two of them is large enough, yeah, they will, you know, still belong to this neighborhood. So I keep making the neighborhood smaller and smaller. But at the same time, can someone, you know, so it's like a game we are playing. You throw in a pair of v1 and v2 at me, okay, I find out v1 minus v2 and I find out this v1 minus v2 is a vector of certain length in the sense of the norm that we have defined in a vector space, right, inner product space. So we know that the inner product of a vector with itself is its norm squared. So you throw in, so it's like we are playing a game. Your job is to give me a pair of v1 and v2 from q1 and q2 respectively. My job is to find an adequate or a suitable neighborhood such that the difference between v1 and v2 does not belong to that neighborhood, right. So you throw in a first set of v1 and v2 at me, I take the difference between this v1 and v2 and I get a new vector, right, and I see that this vector is of a certain length. So can I choose a neighborhood that is small enough such that this vector is not contained within that particular neighborhood that I have chosen? So the first round goes to me, okay. Your next move, so it's like a game of chess, let us say. Next move, you find, oh okay, I have given this fellow a v1 and v2 and he found a neighborhood in which this v1 minus v2 does not belong. So what will your next best strategy be? You will try to choose another pair of v1 v2 such that this time the difference between v1 minus v2, yeah, is such that it's a smaller vector, so that this is now contained in the neighborhood that I had given you in my first move. So first move of chess you make, you give me a v1 and v2, I calculate v1 minus v2, I figure out this is the length of v1 minus v2, let me choose a neighborhood within which this v1 minus v2 cannot be fit in. I make my first move, I say this is my neighborhood, now bring it on. So you say, okay, you found a neighborhood, okay, good luck. Now I am going to pick out another pair of v1 and v2, this is my second move in the game of chess. Second move, I give you another set of v1 and v2 picked from q1 and q2, you give me that is, right. So I get this v1 and v2 and now I find, oh hang on, you are very clever, you have picked out a v1 and v2 such that now this v1 minus v2 actually belongs to this neighborhood I had given you in the first move. So now I have to define this neighborhood. So can I pick now a smaller neighborhood, yeah, can I pick a smaller neighborhood such that now this new v1 minus v2 that I have got does not belong. So I give you my second move, I make my second move, I give you a second neighborhood, yeah, the second neighborhood does not contain this, okay, and of course if it does not contain this this v1 minus v2 that you have given me in the second move, obviously it does not contain the v1 minus v2 from the first move because it is a smaller neighborhood. So likewise we keep making this smaller. If you are both smart players, this is how we should proceed. Ultimately, if these two sets are indeed strictly separated, then I will eventually win, because you will run out of v1 and v2 such that I will ultimately converge on a small neighborhood such that you cannot find any v1 and v2 pair from q1 and q2, so that v1 minus v2 does not belong to this neighborhood and I would have won the game. On the other hand, if they are not strictly separated, right, you can immediately find a particular vector that belongs to both v1 and q1 and q2, and then v1 minus v2 would be 0, and 0 itself is going to be part of its own neighborhood. So you would have finished the game off in the first move itself if you are smart. right? So, if it is strictly separated, I will eventually win the game. If it is not, you will win the game in one move, right. So, that is the way to kind of visualize this description or this definition. Okay. If you again want to draw a picture, well, strictly separated, you have one set Q1 here and another set Q2 over here, right, and you will find that you find any 2 points V1 and V2 between these, any arbitrary points here, yeah, and you will see that the difference between those two will be not be a part of the neighborhood. So, you in this sense, again this is a notion of distance here. So, you find out this distance here, yeah, and you find out a neighborhood that is smaller than this, right, then the difference between those two will not be contained within that neighborhood, but yeah. So, then what happens if they are strictly separated, I can always find a small enough neighborhood such that the difference between a particular choice of vectors which are closest. So, you find out that pair of vectors from Q1 and Q2 which are closest to each other, yeah, in the sense of the norm, right, and I choose a neighborhood that is smaller, like the unit ball's radius in the sense of that norm is smaller. I mean, I am throwing in a lot of terms very loosely here, but at least when we are drawing pictures, then nothing else is sacrosanct anymore. So, I can make use of these terms very frivolously and in a rather casual manner. Yeah, the idea is to understand after all. But anyway, up till here it is reasonably rigorous in the mathematical sense, reasonably rigorous, not absolutely rigorous. Okay. So, this is how we understand the idea of strictly separated sets, all right. The next idea we will now encounter or try to get a handle over is the idea of bounded sets. Okay. Again, you see, in each subsequent definition we are not going to be using any idea other than what we have already encountered earlier. Okay. So, what is a bounded set? So, here is what it is. Suppose Q is a set, is a subset of the vector space V. It is said to be bounded, yeah, this is the definition of bounded set, if there exists a basis for V, say the following basis, say the following basis V1, V2 dot 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 till Vn. Okay. So, it is said to be bounded if there exists a basis corresponding to which, yeah, corresponding to which we have a unit open ball V1, V2, so on so forth, sorry, not a brace bracket, yeah, such that this set Q that we have been given, such that Q is contained within this ball. Yeah. So, here what is the challenge? Again, thinking of it like a game of chess or cards or whatever 2-person game you might think of. What is the challenge here? If you want to check for whether a set is bounded, yeah, you give me a set, all right, you have thrown me a set, so it's your move that you've made. Then what is my job? It's a game that gets over in one move. It's just maybe one show of the hands or whatever, cards or chess, whatever you like. or maybe roll of the die. So here's how it works. So your roll of the die is, you've given me a set Q. In my roll of the die, what I have to do is, I have to figure out some basis subject to which I have this ball, this unit ball corresponding to this basis. Remember, this unit ball depends on the basis, it is very much basis dependent, right. So I cook up this unit ball, and if I am able to cook up this unit ball such that the set that you had thrown at me is contained entirely inside this unit ball, yeah, then I would say that the set you have given me is bounded. On the other hand, if I am unable to get any basis such that the corresponding unit ball for that basis fails to contain, or rather contains the set, yeah. So no matter what ball I can, what basis I choose and the corresponding ball that I construct, the unit ball that I construct, it fails to contain the set that you have given me, then such a set cannot be bounded, okay. So that's how we decide, we play this game to decide whether a set is bounded or not, okay. So this is how we describe a bounded set. So what is the idea here? The idea here, unlike in the previous case where I was cooking up smaller and smaller neighborhoods in each subsequent move, as you gave me this V1 and V2 from the sets Q1 and Q2, I was going on shrinking. If we are both smart players, we are trying to challenge each other to the utmost, eventually I will have to shrink, keep shrinking the size of the neighborhood until the size of the neighborhood is small enough so that no matter what V1 and V2 you give me from Q1 and Q2, the difference between V1 and V2 will not be contained within that small neighborhood. So there the challenge was to sharpen or refine the size of this neighborhood to be small enough. Here on the other hand, the challenge is to cook up a ball that is large enough. So this ball has to be sufficiently large. So that is my challenge here in this game, yeah. So what I am trying to do here is, you give me a set Q, I am trying to cook up a basis subject to which, yeah. So if one particular basis does not work, maybe I just scale every vector in the basis by a particular factor, let us say t, and make this t large and large, larger and larger. So I keep making this ball large and large, so on. If no matter how large I make this ball, I can never contain this set Q, then that set is unbounded. That is it. You have all encountered unbounded sets in the familiar domains that you have, like infinite sets, right. But in topological sense, we really do not want to give it that sort of a particular structure. Yeah, as I said, it is after all arbitrary abstract vector spaces. So I can always cook up a sufficiently large enough ball and a corresponding basis, that is, so that it contains this set Q, then the set Q is said to be bounded, okay. And now the more important definition, when we are dealing with these real numbers and these real sets and all this, then it turns out that the idea of boundedness plus closedness, whatever you might call it, yeah, of a set is identical with compactness. So this is the new term that I am now introducing. So in short, if someone is telling you that a set is compact, here is what you should immediately read. You should immediately understand that that set is, at least in this context of this course here, right, because we are dealing with real numbers here. The particular topology that we have is a vector space over a real field. So what we are going to talk about here is compactness, in the sense that if I tell you that a given subset of the vector space V is compact, within the precincts of this course you should understand it as that the set is bounded. When I say it is bounded, it means there exists some basis such that the unit ball corresponding to that basis contains the set entirely, and also the set is closed. If the set is closed, it means its complement is open. If its complement is open, it means what property must its complement satisfy? Yeah. So you pick out any point in the complement set and cook up neighborhoods around it, and you will see that the intersection of that neighborhood with points in that complement set, yeah, that must be non-empty, yeah, non-trivial, as we have already defined. So you see all these ideas that we have defined here, yeah, we have defined what an open set is, yeah. So an open set means that you have any neighborhood of that point, of any point therein, yeah, and that neighborhood must be entirely contained within that set Q, right. Of course, there is the closure, sorry, I was mistaken there. So, what we are using here is the idea of openness. So, a set is open if the neighborhood of every point of that set is contained entirely within that set, and therefore, its complement is then defined to be closed. So, if you want to test for a set whether it is compact or not, first test is look at its complement and check if it is open, and then check whether it is bounded. Yeah, so, boundedness plus closeness will lead to compactness. Okay. So, with that notion of compactness, we will end today's lecture. In the next lecture, we will maybe give you an important result about these compact sets and the relation between compact sets and why it is easier to check for this condition of strict separation when sets are, at least one of the sets is compact. Okay. And then we will launch into a description of convexity and convex sets thereafter. So, all that is matter that is reserved for the next lecture. Thank you.